Good
Morning.
morning, sir.
Good morning, sir.
Before I start, let me tell you a few things. Uh, I don't know whether you know about concave functions or not. I have sent a write-up yesterday by Gmail. The same story is also true with the convex functions. Holder's inequality can be proved using exponential as well as log. The only difference is log is concave, exponential is convex. For concave, I have sent it. For convex, if you want, you have a look at the some someplace in the net. Wikipedia is the best. I took it from Wikipedia. That's one thing. Second thing I wish to tell you, to do numerical analysis without the knowledge of functional analysis can be little tough. Before that, I'm going to stop my camera because it will improve the audio, bandwidth. Bandwidth of audio will increase if you stop the camera. So I'm stopping the camera. Fourth thing uh, is that it is just not the numerical analysis. Even in the big data, you need to know more about that. It's one chapter on infinite matrices. I don't think I'll get time to do it. I'll send you the material and ask you to uh, submit it as an assignment. One more thing which I wanted to tell you is, will you be interested in a Viva? After 1.5 months or 2 months before the end semester, would you be interested in having the oral exam? 10% weightage, not more. Tell me, want or not? Okay, we will decide at the time when I meet you in the NIT Mizoram. I'm coming on 31st August. Okay.
No, sir.
Okay. The advantage of having a Viva is that when you go out for the, uh, the interviews, especially for placement, it will be very useful. It will be like a training for the placement or for interviews. That's why I said, if you don't wish to have, good enough for me. See, taking a Viva for 10 or 15 minutes for 11 students takes 110 minutes from me. Whereas it takes only 10 minutes from me. That's why I said, it's more work on me than you. Think about it. Okay. Definitely it is voluntary. If you wish, you take it. Otherwise, I will not take the Viva. So that's the. Now, shall I start? I'll start the lecture now. Okay. I'll share the screen. Bishop, there are 10 people, 2 more have to come. Take care of them. Huh? So,
Okay, sir.
pardon? Day for yesterday, we were looking at this inequality, a b less than or equal to 1 over p a raised to p plus 1 over p prime. Somebody wants to join. Just 1 minute. Huh? Somebody wants to join. Okay. This is the inequality which we wanted to show. This is called Young's inequality. P and p prime are conjugate exponents. That is 1 over p plus 1 over p prime equal to 1. So you normally take p greater than 1. If p is 1, you define p prime as infinity. If p is not finite, that's infinite, then you get p prime as 1. Okay, this Holder's inequality, you don't include 1 as well as infinity. Why? Because it's easier to do it for 1 and infinity. I'll come back to it later. This is the inequality, AB less than or equal to 1 over p, etc. So what we used here, log of AB is log of A plus log of B, that is simple. That is equal to 1 over p, so multiply by p and divide by p. 1 over p log A raised to p, multiply by p prime and 1 over p prime. So take the p prime inside log p prime. Now this inequality, 1 over p log AP plus 1 over p prime log b p prime less than or equal to log of 1 over p a raised to p plus 1 over p prime b raised to prime is a consequence of the fact that log is a concave function. Okay. As ln is the log. Whenever you use log or ln, we mean the basis. Okay. All right. So this is a consequence of the concavity. How does it follow from concavity? I have sent a message. I have sent a mail to you. A simple proof. I have checked it and sent it to you. So as a consequence, this is what we have. So log of AB will be less than or equal to log of 1 over p a raised to p 1 over p prime. Now take the inverse of log. Okay. That's exponential. You take the exponential of log AB, that is AB. Take the exponential of this, then you get exponential of this. Again, exponential log goes up. You get 1 over p a raised to p, 1 over p prime b raised to p prime. That's exactly what we wanted to show. So when p is 2, you get the Euclidean metric proof. Okay. So when 1 is less than or equal to p less than or equal to p and p prime is the exponent dual of p, I told you what it is. Then for all xy in Rkn, I equal to 1 to n xi yi is less than or equal to norm of x in LP, small lp, and norm of y in small l. So this is something which you should understand here. This is the 7.1 gives you the definition of norm of p norm of x. This is called the p norm of x. Note here, this x is an element of Rn or Kn. Okay, so the summation is finite. So you don't have to worry about convergence and whatnot. What happens when n is not finite? I'll give you. So first we prove the Holder's inequality in finite dimension and go through a limit to the infinite dimension. So this is what the story is. If x is 0 or y equals 0, then the inequality is obvious. Okay. So we assume x and y not 0, and p strictly lies between 1 and infinity. Now whatever inequality we have shown here, okay, this inequality. So you take a equal to xi and b equal to yi, and you put down that here, and you divide it by 1 over norm xp raised to p, this one. So this will be equal to 1 over xp raised to p, norm of uh, I equal to 1 to n. You understand this, no? This step. This is independent of I. Okay, so you can take it if you want inside. So apply the Holder's inequality for mod xi yi, that is A equal to mod xi yi. Apply that Holder's, whatever the Young's inequality, divide by norm xp raised to p and sum it up. This is what you get. So when you do a bit, little bit of, this is what you pull this inside because it's independent of So this will be less than or equal to whatever the Young's inequality. So the last step, less than or equal to this, follows by the Young's inequality. Now the rest is all just simple. So you remove this 1 over p here and summation of a plus b is summation of a plus b. So the summation spreads over the two elements. So you get a summation of this here, summation of this here. And you do a little bit of again calculation. You take out this p out and then this xp raised to p, that also out. That you can take it out because this is independent of I. So this comes out of the summation. So what you get is 1 over p, x raised to p, this plus this. And that is equal to 1 over p plus 1 over p prime equal to 1. And what you should understand here is that this 1 over p plus 1 over p prime equal to 1 is used in the concavity definition. That's one thing. So look at the first step. Where did we start? We started here. Okay, 1 over x raised to p, 1 over x is summation x over y. So this is equal to 1 here, the last step. So what you push this x raised to p, y raised to p on the right side, then what you get is summation I equal to 1 to n mod xi yi is less than or equal to the LP norm of x into LP norm of y. Just push this on the right side after the law. You can push it because this is positive. If it was negative, then the inequality would have changed. Anyway, so if you push this here, what you get is actually this. This is what we wanted to show. Okay, this is the LP norm of P, and this is the simple proof of Holder's inequality. Holder's inequality plays an important role, especially if you want to show the Cauchy-Schwarz. This is exactly Cauchy-Schwarz inequality when P is true. Okay, through the inner product. But the question is that in the inner product case, P has to be true. The question can be asked, what if P is not true? Before I start the next theorem, let me stop for a while. Ask a simple question to you. Am I talking too fast? Should I talk slow? Hello?
Yes, sir.
Huh? Should I slow down?
Yes, sir.
You
Yes,
see,
sir.
whatever correct.
Sure.
Yeah. Tell me. Repeat. There's an issue in the online classes because I don't see you in person. So sometimes, if I'm talking too fast, I'll slow it down for a while. There is a way of thinking that a teacher does. There is a way of thinking student grasps. Unless it coincides, the teaching will be gone. That's why I am asking you. One of the reasons why you don't grasp is that teacher is talking too fast. That's the reason why I asked you, shall I slow down? Feel free.
Yes, sir.
Okay, thank you. I'll slow down. So if next theorem is the what is called what is the connection between the LP norm of an element P and the LQ norm of P. The only condition that you take is the one lies between 1 and infinity. The proof for these inequalities for P equal to 1 and P equal to infinity normally are simple. It is not given. So it is normally given to the student as an exercise. That's what he writes here. So what we will do is that we will show the uh, proof when P actually lies between 1 and infinity. Okay? What does this tell you? This tells you the two norms are equivalent. Okay? If you have convergence in the LQ norm, it will converge in LP norm also. If it converges in LP norm, it will converge in LQ norm also. LP norm gives you a metric, what we call as the LP metric. LQ norm gives a metric called LQ metric. Point is that if something converges in LP norm, you found only if it converges in LQ norm, provided 1 is less than or equal to P, less than or equal to infinity. This is normally called in mathematics as they are equivalent. Doesn't mean anything now, whether you take this way or not. When I am in Mizoram, I will let you know more on the topology of this. Okay. What it says is the metric, the topology generated by the LP norm. I am referring to the metric topology, and the metric topology generated by LQ norm. That's it. That's one of the problems in the assignment sheet. Draw the open spheres in LP and LQ norm. Okay. What does that example simply say? It says that when you take P equal to 2, the open ball looks like a circle if you are interested in the two dimension or a disk. But if you take P equal to 1, it may not be circle. It could be a rhombus, it could be a square. So what you do is you draw the unit sphere in the norm P equal to 1, P equal to 2, P equal to infinity. That's one of the problems in the assignment. That will give you more geometrically speaking. What it says is if you have a square or a rhombus, you can inscribe a sphere or a disk. If you have a disk, you can inscribe a square or a rhombus. That is what geometrically this means, whatever this inequality 7.2. It's very important that you should know it. And the second thing it says is the above inequalities are optimal. That means you cannot have any other constant a here, and instead of n raised to q minus p over n over q, cannot have something else. That is a times norm of x2 less than or equal to norm xt less than or equal to b times this. Then the least amount of b is n raised to q minus p over p by q. That is the meaning of saying the above inequalities are optimal. These are the best constants you can think. Okay, you can increase this whatever this constant is, but you can't decrease this. Okay, proof is not a very difficult proof. Okay, just the triangular inequality, and so you dispose of the matter for t equal to 1 to infinity, that's left as exercise. Now you consider 1 less than t less than infinity. Since the norm of LP norm of x is always non-negative, it is 0 if and only if xi is 0. Xi is 0 for all I equal to 1 to n. So if x is 0 and alpha is in k, then this is an obvious inequality. Okay? Nothing great about that. So it remains to prove the triangle inequality for xy in Kn using Holder's inequality. So after going through this bit of calculation, computation, so you take mod of x plus y raised to p. By definition, this is nothing but I equal to 1 to n. So here you use the definition. I equal to 1 xi plus yi raised to p. Right? This is the definition of LP norm. Now this x raised to xi plus yi raised to p, you write it as mod xi plus yi into mod of xi plus yi raised to p minus 1. So you split this p into p minus 1. Okay, p and p minus 1. So this p greater than 1 is used here. Alright. Okay. Now you have summation I equal to 1 to n mod of xi plus yi into mod of xi plus yi raised to p minus 1. This is like ai, this is like bi. So this is I equal to 1 to n ai into bi. Apply the Holder's inequality. Put it down here. Now first you split this one. Okay. This xi into this one and then yi into this one. So this is exactly splitting this bracket here, whatever the bracket you have. That's not a big issue here. Okay. What I'm saying is mod of xi plus yi is less than or equal to mod xi plus yi. So mod xi into this one is here. Mod yi into this one is the second term. The moment you have mod xi into this one, call mod xi as ei, call mod xi plus yi raised to p minus 1 as bi. Apply the Holder's inequality. Okay, so you get a whatever the Holder's inequality you get here is precisely the consequence of the Holder's inequality. Okay, you apply the Holder's inequality for the second one also, and what you get is this term mod of xi plus yi raised to p minus 1 raised to p mod xi plus yi raised to p minus 1 raised to p 1 over p is a common factor. Take the common factor out. So what you get is the x p norm of x plus p norm of y. This is what you have. So what we note here is that p prime is 1 minus 1 over p raised to this comes out from 1 over p plus 1 over p prime equal to 1 conjugate. Okay. So take the common factor here. What you get is p minus 1 on the top divided by p. But there is a minus 1 here. So it becomes p over p minus 1. So p prime will be actually p over p minus 1. Push this value of p prime into this last inequality. So what you get here is precisely mod of y raised to p will be less than or equal to norm of xp plus norm of yp, this is common, and x plus y by p into p minus 1. If p over p minus 1 comes here, you replace this what is called the. So if x plus y is not 0, we get a triangular inequality. The LP norm of x plus y less than or equal to LP norm of p plus LP norm of y. Take p equal to 2 is exactly what the Euclidean norm is, right? Summation xi plus yi square less than square I equal to 1 to infinity raised to half is less than or equal to summation of the summation xi raised to 2, etc. etc. This is the triangular inequality. Okay, with the p number. When p is 2, you get the what is called the Euclidean number. The inequality is obvious if x plus y is 0. Why is this story that we are talking about? We are using the fact if x plus y is not 0, then you divide by that. This x plus y raised to p minus 1 over t, I will push it on the left side here. And when you push it on the left side, I have to make sure that x plus y is not 0. If x plus y is not 0, then x plus y raised to p minus 1 is not 0. Push it on the left side. You get x plus y raised to p divided by x plus y raised to p minus 1. Apply the same inequality, p prime equal to p over p minus 1. You get this x plus y, p norm is both. If x plus y is 0, suppose x plus y is 0, because you have to consider two cases, x plus y is 0 and x plus y is not 0. If x plus y is 0, this is 0, this is 0. So inequality is obvious. Right? So hence, if x plus y is not 0, we are saying, what if x plus y is 0? Inequality is obvious. So inequality is true, whether x plus y is 0 or x plus y is not 0. So this is the inequality that we are looking at. So we now show the inequality 7.3. It is 7.3. This is the inequality. Okay, not a difficult proof. Okay, about optimality. Those who are doing optimization, this inequality will be useful. Okay, let me not worry about that optimality. I am not going to use it in my function analysis course. It's an extra information that we have. This is the what is called basic groundwork. Remember what we were doing. We were defining a nonlinear space. We were defining a convergence of the nonlinear space, convergence of sequences in nonlinear space, etc. etc. But we have not given any example till now. So first thing that we do here is that we give examples of sequences, space of sequences. We also look at spaces of functions also. Let me stop. Let me just digress myself here. What is a digression? If you are working in data analysis, if your data is discrete, then you get space of sequences. If the data is continuous, then what you get is the sequence, the spaces of functions. So this is essentially the basic requirement in the structure of the data analysis when the data is discrete or when the data is continuous. Any questions?
No, sir.
Hmm? Any questions?
No.
Whatever has been said is clear. Saurabh Gupta has left the meeting. ऐसे कैसे होता है ऋषभ?
I don't know. Maybe, sir, they are coming from hostel, sir. 9:30 bus. That's why maybe their network is so.
Then why is the class is held from 9 o'clock? Saurabh, can you talk to Nikhil and ask him to manage something like this. Is there a bus at 9 also?
Okay, sir. Okay, sir. Next,
Or tell whomsoever is,
from other hostel, sir.
ask them to come here at 9 o'clock here.
Okay, okay, sir. Okay, sir. I will inform everyone, sir.
Yeah, what I was told is that quite a few people here are also interested in data sciences. That is why I am also trying to link functional analysis course with the data sciences, right? So way back in 1983 or 4, I gave this course in IIT Kanpur, and one student from India had joined. Now he is in the United States doing some on the Teachers' Day. He sent a message saying that now we understand why functional analysis is important. If you want to understand infinite by infinite matrices, it's essential that we understand functional analysis. And then he was saying, thankful to you that I attended your course. Now I understand the importance. I am just giving you the input of a student who is in data science. So that this course, I want to link it with some amount of data science. Not that I don't know much on data sciences anyway. All right, so I keep telling this. Second thing I will also want to tell you that many times when you do numerical analysis, you do on non-smooth data. When you do on non-smooth data, continuous functions will not work. You have to work with L2 functions. For that, basic theory that you should know is the function analysis. At least this representation up to that, which is what I want to cover in this course. I don't know what's the idea that the IIT, NIT, Mizoram has asked you to take this course. I'll find out from your director, Sundar, what is the story here. Okay? If you have any question up till this point, what I'm doing is a basic requirement for doing the essentially. I want to give you, not I want to give you. The answer is giving examples of non-linear spaces. These are extremely important. These are extremely useful. These are the topics on which you will be asked questions when you go for an interview. It could be for PhD, it could be for a faculty position. That is why I am saying please concentrate more. If you have difficulty, let me know. I will repeat. Okay? Go back to share.
Okay, sir.
Okay. So the spaces of sequences. So here we discuss spaces of sequence. Most of you have seen this in
Sir,
physics.
one more. Sir,
Go ahead.
excuse me, sir.
Go ahead.
Sir, is it possible to write on the white paper board something like that, sir, to explain?
If you want something to be explained,
Like,
tell me, unless you tell me what is to be explained, how do I explain to you? I have the Wacom tablet here. I can write on that. Good. I don't know about the
okay, sir.
board stuff,
Like
but I can
at
write on
the
the smart
previous
tablet.
class,
Yeah, previous
I
class.
like the previous class you have done on the white paper and writing and explain like
Yeah,
that,
yeah,
sir.
I have the tablet
If is
here.
it possible, then
Yeah, yeah, it's
I think
possible. Definitely it's possible.
okay.
It is with
Then
me here. I
then
will do that.
I think so. It will be more
My
okay, sir.
question is that when you have some doubt somewhere, if you ask me that, then I can write on the board. If you have no doubts at all, that is why I stopped after the holders inequality. If you have any doubts, since you are not saying you have any doubts, I understand that you have understood everything. So if you want to have some whiteboard, definitely next time I will push it. This time you leave it, okay? From the next
Okay,
class,
okay, sir.
yeah, it's already there. I have to open a PPT, nothing more. Sure, definitely.
Okay, okay, sir.
Stop
Okay,
me.
sir. Thank you, sir.
Yeah, welcome. Stop me if you don't understand. I will repeat it. Okay. NIT Mizoram. Just wait. I'm looking at the NIT Mizoram. Miscellaneous matters folder somewhere. Takes a bit of time to open the file. Just to hold on. Before we go ahead, let me explain to you what is RN and L2, etc., etc. Okay. Just hold for 1 minute. You see, shifting from talking to writing, I have to close one file and open another file. And opening that file, sometimes it takes time. So just hold on. I will give you.
Okay, sir. If we have any doubts, sir, then I will ask. We will ask. Then you can explain on why.
Yeah, you're opening the file, it is taking time. Anyway, just wait, just wait. It is open. This is the holders inequality from the book of Cauchy. I have sent it yesterday. Okay. Here they use the concavity or convexity in the uh, whatever no, concavity for proving this theorem, the dancer's book. This is the book of Cauchy, where he uses this uh, integral ab less than or equal to t raised to p minus 1, d raised to t, etc. This is what I have sent to you. This is an alternative proof for the Holder's inequality without using the log function. This is through integration. Okay, you can think of seeing this proof. This is exactly, I didn't want to do it in the class because it is too simple. Okay. Is it visible? First question is, what is this Rn? You think or you know it as the n tuple, right? Can you see it in a different way? What I'm saying is, you take the set Sn equal to 1, 2, 3, n. Okay. So if you take this map X, X is a map from Sn to R, right? So this becomes set of all maps from this Sn. Clear? This is another way of defining Rn. How do you define this Rn? You have to define it as an n tuple. How do you know an n tuple exists? Essentially what we are saying is, you have R here, okay, and now you are looking at, let me do it for 2, okay, you are looking at R cross 2. What is R cross R? This is where the trouble is, okay. R cross R is a set of all ordered pairs. Then the question is, what is an ordered pair? There's another way of doing it, is that you can use axiom of choice. You can use axiom of choice. That is, if you have a set like this, it need not be, you can take any set AB, okay. Then you can think of A cross B. So what is this A cross B? This is nothing but set of all alpha beta, alpha in A, beta in B. This set exists because of the axiom of choice. What is so important about this definition? This definition is easy because when you want to take, if you look at a sequence, all right. So when you want to look at a sequence, new slide. When you look at a new slide here, okay. So when you look at a sequence, what is a sequence? It is x1, x2, xn, and it goes on. This you write it as with a bracket xn. What is this? This is nothing but a map x from the natural numbers to R. So what is a sequence? It's a map from natural numbers to R is called as. So this x is called a sequence, a definition. So what is the difference between y1, y2, yn? y1, y2, yn has finite number of components, whereas this has infinite number of components, as many as you have in n. Okay, this is the discrete case. What's a continuous case? You look at a function f from 0, 1 to R. This is a continuous distribution. Okay. First one is discrete. 1, 2, 3, 4, n dot dot. Whereas in this case, the function that we are looking at is an interval. This is something like 0 to 1. This is uncountable. So the value is defined at some point here at x. You can take an example like sin x, okay? So here the value takes at discrete points, whereas here the value of the function or the whatever the f is, it takes on at every point on the interval 0, 1. So this becomes a continuous case. Whatever that continuity means, okay? This is the, so when we are dealing with a sequence space, like, so this can be, so when you have y1, y2, yn, then you attach a length to it, mod yi square, finite. This is finite because it's by definition, it's a finite sum. How do you have a metric here? Then you can ask me a question, sir, why do you want to have a metric? Metric gives you some idea of the length, etc. That is what you need for error analysis. So here, if you generalize this, what you get is summation mod xi square finite. Who told you that this is finite? Huh? Right? So what you do is, you take L2 of R. This is all xn's such that summation mod xi square is finite. You take such element that is called L2R. This is the generalization. This L2R is the generalization. So this is normally called L2n. R means it's an infinite dimension. Why should it convert? Is different. You see, for example, you take the element 1, 1, 1. Okay, all elements are 1. This is in this sequence space, but unfortunately, the summation is infinite. So this element will not belong to it. But we need that, without which we can't work on the functionality. We need completeness, etc. All right. So this, whatever the comment I am making here, can help you a bit more, in what I was talking to you till now. Is this what you wanted, Rishabh?
Yes, sir.
Now, is the difference between Rn and L2, is it clear?
Yes, sir.
Good. Next time I'll do the metric structure of the infinite dimension. Finite dimension is almost over. Okay. Have a good
Okay,
day.
sir.
Bye. Next week we'll meet.
Okay, sir. Thank you, sir.
Have a good day.